Hey guys, let's have a look at a particular question. I'll start by reading the data given. The figure below shows a block of mass M, that is block 1, that's attached to one end of an ideal spring of spring constant or force constant K and a natural length L. So the natural length L is a resting length, or the length at which there is neither a compressive nor an expansive force applied by the spring. The block is pushed so that it compresses the spring to 3/4 of its natural length and then is released from rest. Just as a spring has extended to its natural length L, the attached block collides with another block at rest on the edge of a frictionless table. So friction can be ignored. Let me just make note of that. Friction force Fr can be ignored for this particular problem. When block 1 collides with block 2, half the kinetic energy is lost to heat. The other half of the block 1's kinetic energy at impact is divided between block 1 and 2. The collision sends block 2 over the edge of the table, where it falls a vertical distance h, landing at a horizontal distance r. So projectile motion. Now, what is the acceleration of block 1 at the moment it's released from rest from initial position? Write your answers in terms of K, L, and M. So let's start by answering part A to begin with. Now, so acceleration is force by mass, Newton's law. And force applied on block 1 is nothing but the compressive or the expansive force of the spring. Since it's compressed to 3/4 of its original length, the actual change in length, delta x, is 1/4 L. So since F is equal to kx, K into delta x is 1/4 of L. So this gives me the force divided by M. Simplified, the formula becomes KL divided by 4M. So this is the acceleration. Moving on to part B. If V1 is the velocity of block 1 before impact, show that the velocity of block 1 after impact is half V1. Here we notice that there is no external force, which means conservation of momentum. M1U1 plus M2U2 will be equal to M1V1 plus M2V2 can be used. So substituting, we can write the formula as M1 V1. Since this say the velocity V1 is its value before impact plus 0. The reason I'm writing 0 is because block M2 is at a state of rest. Now after collision, let's assume that block 1 had a mass of V1 dash. So M V1 dash plus block 2 had a velocity of M V2 dash. Simplifying, we get V1 equals V1 dash plus V2 dash. This does not help simplify the question. We also can, however, use the relationship given for kinetic energy. They say that the block 1's kinetic energy is such that half of it is lost to heat or any other resistive forces, and the other half is converted to the kinetic energy of the other two blocks. So from kinetic energy distribution, I end up with the following velocity equations. That is, V1 the whole square is equal to 2 V1 dash the whole square plus 2 V2 dash the whole square. Now, simplifying these two equations, we can get the relationship such that we finally get V1 dash will be equal to V2 dash will be equal to half of V1. This is the required answer. Now, part C asks us, determine the amplitude of oscillations of block 1 after block 2 has left the table. Write your answer in terms of L only. So they say that it will execute oscillations. For it to be able to execute oscillations, the kinetic energy is converted into elastic potential energy of the spring. And by that logic, we notice that the kinetic energy half mv square, half mv square or v1 dash the whole square in this case, which is its velocity after collision, is equivalent to half k. Let's assume the amplitude with which it oscillates is a dash. So a dash the whole square. Now, I know that v1 dash the whole square can be, or v1 dash can be substituted as half v1. And through these substitutions, I can get the final amplitude as equal to a dash whole square is equivalent to 1/16 of k L square over 4k, which then simplifies as L square over 64, giving me the value of E dash as L over 8. Now, moving on to part T. Determine the period of oscillations of block 1 after the collision. Writing your answers answer in terms of T naught, the period of oscillation that block 1 would have had if it did not collide with block 2. Now, we notice, let me write the equation before I tell you this. So time period for horizontal spring mass system is 2 pi root m by k. So by this logic, we notice that the spring constant k is what the time period depends on, and also the mass. And since neither the mass nor the spring constant k changes, the time period t will remain same as the previous value in t and will not change. Now, find an expression for r in terms of hk. Okay, this is projectile motion. For projectile motion, we have two equations. For horizontal part, we have x is equal to u cos theta t. For vertical motion, y equals u sin theta into t. It's plus or minus depending on whether the body is going up or going down. Now block 2 is just going down, so it's going to be plus half. You rewrite this plus half g t square. Now I know that the angle of projection is theta, which is 0 in this case. I know that the vertical height is h, the horizontal distance is r, and I know the velocity is of the block is v2 dash, which is half v1. Now, I know that r, horizontal range r, can and will be found out through a standard formula. We have formulas, standard formulas for maximum horizontal range. We have it for maximum height. We also have it for total time of flight. So through simple substitutions for the equation or through standard formula, we can find out that r as a formula, r is equal to half square root k L square over 16m times root 2h by g. We can just simplify the equation, but the answer remains the